Let's talk about the equilibrium of a body. Okay, so we have already discussed equilibrium of a body in laws of motion. Now there would be two kinds of equilibriums. One is the translational equilibrium and other is the rotational equilibrium. So for translational equilibrium, what is the condition? So we have seen the condition for translational equilibrium: sum of all forces acting on a body is equal to 0, right? Then if body is at rest, it remains at rest. If it is moving in some direction, okay, with some velocity, it keeps on moving with the same speed or same velocity in the same direction if net force acting on the body is equal to 0. Okay, similarly there is rotational equilibrium. So if body is at rest or it is rotating about a fixed axis with some angular velocity, it will keep on doing that. Okay, if it is at rest, it will remain at rest. If it is rotating with some angular velocity about a fixed axis, it will keep on rotating about that same axis with the same angular velocity unless there is some external torque exerted on the body. Okay, so for translational equilibrium, net force is equal to 0. Net force acting on body is equal to 0, or you can say sum of all forces acting on the body. So I goes from 1 to n, summation of fi bar is equal to 0. And for rotational equilibrium, we have net torque acting on the body equal to 0. Okay, so sum of all torques due to all forces acting on the body is equal to, sorry, it's equal to 0. Okay, so this is the condition for translational and rotational equilibrium. So we'll see problems based upon that, but before that there is one more little concept, and it is of center of gravity. Okay, so we know what is center of mass now. So let's discuss center of gravity. So center of gravity is such a point about which all gravitational torques on a body is equal to 0. Sum of all gravitational torques acting on body is equal to 0. So for an example, you might have done this trick that or you might have seen some students doing this trick. They balance a book on one finger and they also rotate it, right? So which is that point about which they balance the book? It's the center of gravity. Yeah. So let's consider a book, or any body for that matter, and you want to pivot that body. Okay, you want to pivot that body such that it doesn't topple. Okay, such that the body doesn't topple. When will it topple? If there is some unbalanced gravitational torque. Okay, so let's suppose this body is made up of n number of masses. So there is this first mass, second mass, third mass, fourth mass, fifth mass, sixth mass, seventh mass, so on and so forth. So now you draw, let's suppose this is the center of gravity. So what will happen? So you will draw position vectors of all these masses from this point, okay, and there will be gravitational force acting downwards, okay, on all those masses. Okay, so this is m1, m2, m3, so on and so forth. So there will be gravitational force acting downwards. like this, right? So this is the gravitational force, and this is the position vector about this point, suppose. So what will be the direction of torque? The direction of torque will be r bar cross f bar. Okay, it will be pointing outwards, if you see. Okay, r is towards left, f is downwards, so r cross f, it is towards left. Okay, r cross f, right, it's towards me, and if I do it here, it is upwards, sorry. Okay, so now there will be torques due to all such forces. Okay, so this force, the gravitational force acting on this mass, it will try to rotate the body in downwards direction, you can say. Okay, so gravitational force on this mass, it will try to rotate the body like this, downwards direction here. Here you can say it is in anti-clockwise direction, here it is clockwise direction. So you have to balance all those torques. Okay, if all the torques are balanced, then that point is known as what? That point is known as the center of gravity. So what is center of gravity? Center of gravity, it is a point about which all the gravitational torques acting on body, acting on body sum up to 0. Okay, so if you add gravitational torque about that point acting on all masses of the body, then what will you get? You will get 0. Okay, so this is the concept of center of gravity. Now for symmetric objects, the center of mass and center of gravity will coincide if objects are symmetrical. If they are not symmetrical, center of mass and center of gravity might be different. So is it clear? One more small concept and that is the concept of lever. Okay, so what is a lever? For an example, you want to lift a heavy load. Okay, you want to lift a heavy load, right? So this is a load, suppose, that you want to lift. Okay, and you will lift that pulling this arm. Okay, so let's suppose this is a balance. I'm sorry. Okay, let's suppose this is mechanical balance. So it's pivoted about this point, the midpoint actually. Okay, so this is mechanical balance. Now there is a load to be lifted, which you will keep in this arm. Okay, in this span. Okay, and you will exert some force on this side, or you will keep some weights on the other side. Now what happens? They get balanced. Okay, they get balanced when both the weights are equal. Okay, when this weight and this weight is equal. So now what you can do is you can balance them just shifting this pivot towards left and putting very small weight on the right hand side. Okay, on the right hand side pan. So how is this possible? So what you are actually doing is you are balancing the gravitational torques, I mean. Okay, so see, so now if we think about a normal balance, normal mechanical balance, so it is pivoted at the midpoint. The load or the objects to be lifted, they are kept in this pan, suppose. The weights are kept in the other pan. Okay, so when weight of these objects become equal to weight of this weight in the other pan, then what happens? It is balanced. Okay, the balance is balanced, right? Now you can achieve this thing. I mean, you can lift, sorry, you can lift this load with very small weight or very small effort in the other pan. How come? You just have to shift the pivot towards left, a little bit towards left. Okay. So for an example, so here this is L by 2 and L by 2. So there will be some torque due to this load. So weight of these objects is known as the load. Okay. And here the weight that you are putting in the right hand side pan, we'll call it effort. Okay. So now see, here the load and weight will be, sorry, the load will be equal to effort, or effort needed is equal to load if this distance is equal to this distance. But now what we'll do is we'll shift it towards left, or I will draw a different diagram. Okay. So actually what we are doing here is, see, there will be some torque, the gravitational torque due to this load. Okay. And what will be its direction? Its direction will be anti-clockwise. See, this is R bar and this is F bar. Gravitational force is downwards only. So R bar is directed like this, F bar is like this. So this load, it will try to rotate the pan, okay, the balance in anti-clockwise sense. Now the weight in the effort pan, okay, the weight that you are putting in the effort pan, it will try to rotate it in clockwise sense. Okay, see, this is R bar and this is F bar. So R bar cross F bar, it's in clockwise sense. It is rotating in clockwise sense, right? So now when the weights are balanced, it will not rotate. Okay, the balance will be balanced and it will not rotate, right? Because torques are balanced. What is balanced? Torques are balanced. So we can achieve the same thing. Okay, we can achieve the same thing. So let's suppose, let's call this L1 and this is L2. Okay, now the weight that you are putting in this arm, let's call it W1. Okay, and weight that you are putting in the other arm, let's call it W2, right? So now see, if tau1 is equal to tau2, the balance will be balanced. Okay, so what is tau1? It is L1 multiplied by W1 multiplied by sine of theta, you can say, but theta is equal to what? It's 90 degrees. Okay, theta is equal to 90 degrees, right? So this is equal to, when this is equal to L2 multiplied by W2, okay, then the balance will be balanced and the torques will also be balanced, right? So now you can see that W1 divided by W2 is equal to what? L2 upon L1. W1 divided by W2 is equal to what? L2 upon L1. So this length is known as the load arm. Okay, this length is known as the load arm and this length is known as the effort arm. Okay, and see, if you have large effort arm, also called as lever, okay, if you have large effort arm, let's suppose this is 10 times bigger than this one, then you can see L2 upon L1 is suppose 10, then W1 will be equal to what? 10 times W2. So that means it will be balanced, or you can you can lift 10 times 10 times as much weight. Okay, if effort arm is equal to what? 10 times as much long as the load arm. So is it clear? So you can lift 100 Newton weight by applying force of 1 Newton if the effort arm is 100 times longer than the load arm. Okay. So this simple mechanism is known as lever. Alright. And this ratio of the effort arm to the load arm, it is known as the mechanical advantage. Length of the effort arm. Okay. So L2 upon L1 is known as what? Sorry. It is known as mechanical advantage. Okay. So how many times, sorry, how many times the effort is multiplied? Okay. So how big of a load you can lift? Okay. Applying some effort, it is known as mechanical advantage. Okay. All right. So let us discuss some problems based upon this. So this one is from NEET 2017. Which of the following statements are correct? Center of mass of a body always coincides with the center of gravity of the body. Is it correct? Is it true? No. Good. Center of mass of a body is a point at which the total gravitational torque of body is zero. It's not true. It is center of gravity. Right. Next one, a couple on a body produces both translational and rotational motion in body. Not true. Okay, it produces only the rotational effect. Okay. And last one, mechanical advantage greater than 1 means that small effort can be used to lift a large load. Okay, so this one is correct, not option D. Option 4 is correct. And actually none of these options is correct, only fourth is correct. Okay, so this is the mistake. So let's see next question. A rod of weight W is supported by two parallel knife edges A and B and is in equilibrium in the horizontal position. It is in equilibrium in horizontal position. The knives are at distance D from each other. The center of mass of the rod is at distance x from A. The normal reaction on A is. Okay. So this is very simple question. There is a rod of weight W. Okay. And it will have some length. Now its weight will act downwards. From which point? From the center of gravity. Right? From the center of gravity. And because this is symmetric body, it will act downwards from its midpoint only. Now you are using two knife edges at A and B. So let's suppose this is point A and this is point B. You are using two knife edges to support it. So they will exert some normal reactions which will be vertically upwards. Okay. So let's suppose normal reaction due to the first one is N1, normal reaction due to the second one is N2. Okay. So this normal reaction due to the first one is suppose N1, normal reaction due to the second one is N2. This is N1, this is N2. Okay. So now the distance between A and B, that is two knives, is D. Okay, that distance is D. Right, this distance is D. It's given. and the center of mass of the rod is at distance x from A. Okay, so we don't know whether it's symmetric or not. Okay, if rod is symmetric, then it will act at the midpoint. Okay, so this distance is given, this distance is x, right? So how much would be this distance? This distance will be equal to what? D minus x. This distance will be equal to D minus x. Okay, so now what we can do is we have to find out normal reaction on A. So we want to find out N1. Okay, we want to find out N1. Now short trick here is to take moments of forces about the second point, because we don't need N2, right? So for rotational equilibrium, what do you need? Torque due to W and torque due to N1 should be balanced. Okay, so let's take torque due to all the forces about point B. Okay, they are equal to. So how much is distance of W? It is D minus, sorry, it is D minus X, right? So D minus X multiplied by W multiplied by sine of 90, which is 1. Okay, and this rotation, you can see this rotation is in which sense? So W is towards left, right? It is, I mean, W is on the left side of this point B. Okay, so this is the position vector, this is W, so R cross F. So this W will rotate the rod in anti-clockwise sense. Okay, see the other one, other torque. So other torque is due to this knife, okay, which is N1 at A, right? So sorry, the normal reaction is N1, which is at distance D from point B. And in what direction? It is rotating the body. So this is upwards, and this is, see, the position vector is towards left. Okay, so this is R and this is F. So R cross F, it is rotating the body in clockwise sense, right? This is clockwise sense. So if we take anti-clockwise rotation as positive, then clockwise would be negative. Okay, the clockwise would be negative. So minus, how much is distance of this force from point B? It is D. D multiplied by this force is N1, right? And this torque must be equal to 0 if the body is balanced. So now we can take this D times N1 on other side. So we get D times N1 is equal to D minus X times W, and we want N1 only. So it is N1 is just equal to D minus X divided by D times W. Okay, so option B is the answer. Yeah. So this question is repeated in 1998, 2012. ABC is equilateral triangle, an equilateral triangle with O as its center. O is the center. F1, F2, F3 represent three forces acting on the sides AB, BC and AC respectively. If the total torque about O is 0, then the magnitude of F3 is. So total torque is 0, right? How much is F3 is the question. So see, let's find out total torque. So this F1 is at some distance from the from what? The center, actually centroid. Okay, so it is at some distance. F2 and F3 are also at the same distance. Okay, but now see, the action of force is different. So if you take this as its position vector, so now F1 is rotating this triangle in anti-clockwise sense. You can see this is R, this is F1. So R cross F, if you take, it is rotating the triangle in anticlockwise sense, right? What about F2? So F2 is also rotating the triangle in anticlockwise sense. Okay, it is also rotating the triangle in anticlockwise sense. And what about F3? So let's draw its position vector. It will be like this. So if you take R cross F, this is R, R3, you can say R3 cross F, it is rotating the body in clockwise sense. Okay, they are at the same distance. They are at the same distance. Okay, so if you can think this way, or you can say this angle is theta, this angle is theta. How much will be this angle, by the way? This will be 30 degrees, right? So this will be angle bisector. This angle is 60, so this is 30, so this angle will be 30 degrees, right? So angle between R1 and F1 is 30 degrees. Angle between R2 and F2 is also 30 degrees, but angle between R3 and F3 is not 30 degrees. It is 180 minus 30, right? It's 180 minus 30. So you can say tau 1 plus tau 2 plus tau 3 is equal to 0. Okay, so how much is tau 1? It is it is R1 into F1 multiplied by sine of 30 degrees, okay, plus R2 F2 multiplied by sine of 30 degrees plus R3 F3 multiplied by sine of 150 degrees. This is equal to 0. And sine of 150 is minus sine 30. Okay, so this is the rule. Sine of 180 minus theta is equal to minus sine theta, right? Sine of 180 minus 30 is sine of 150 is sine of 180 minus 30. So it is equal to minus sine 30. Okay, so we can take sine 30 common and we can cancel it out. So, and also R1 is equal to R2 is equal to R3, right? So we can take that also common and cancel it out. So we have F1 plus F2 minus F3 is equal to 0, or you can say F1 F3 is equal to F1 plus F2. Okay, F3 is equal to F1 plus F2. Option A. This is most this is simplest question. Couple produces. Couple produces what? Linear and rotational motion, no motion, purely linear motion, purely rotational motion. Right. Option D. Purely rotational motion. Next question. This is from NEET 2013. A rod PQ of mass m and length L is hinged at P. So here is P. The rod is kept horizontal. It is kept horizontal by a massless string tied to point Q. So it is kept horizontal. Okay, it is hinged at this point, and it is connected to the string, massless string. Okay, and because of that it is horizontal. So when string is cut, the initial angular acceleration of the rod is. So if you cut the string, what will happen? There will be some angular acceleration. So see, this is a rod, suppose it is hinged at this point. It is free to rotate about this point, but it is held at this point. Okay, so it will not fall from this point, right? But it can rotate, and now you are supporting it by means of this thread or a string at the other point. If you release it from there, what will happen? It will rotate like this. Okay, so the rod rotates like this. It rotates like this. So what will be its initial angular acceleration? Okay, angular acceleration at starting point. This is the question. which is very simple. See, so when you cut this string is cut. Now, what are the forces acting on it? So it is hinged at this point. Okay. So there is only one force, which is the gravitational force, and which will act from the center of gravity. Okay, L by 2 of the rod, right? And therefore, how much would be the torque? So torque is equal to L by 2 multiplied by its weight. So its mass is m. So weight will be equal to what? M multiplied by g, right? This much is torque. And we want angular acceleration. So torque is also equal to I multiplied by alpha. Okay. So it will rotate about this point, right? It will rotate about this point. Okay, point P. So torque is also equal to what? I multiplied by alpha. I is the moment of inertia. Now we have to use correct formula for moment of inertia. There is one formula, ml square upon 12. Okay, which is about an axis which passes through the center. We don't want that. We want a formula for moment of inertia about this axis which passes through what? One of its edges. So what is that formula? I is equal to what? Okay, so first of all I will equate this. I alpha equals to, because this is torque is I alpha, it's equal to what? L by 2 multiplied by mg. So what is formula for moment of inertia for uh, for a rod for the axis which passes through its edge? It is ml square by 3. Okay, it is equal to ml square divided by 3. So ml square by 3 multiplied by L alpha is L by 2 multiplied by mg. So m gets cancelled. Then what else? L gets cancelled with this one. Okay, one L will be left here, and that you can move on the other side. This 3 you can move on the other side. So alpha equals to 3 will go to the numerator, 3 by 2 g upon L. Okay, option C is the answer. Right, option C. Very good. A uniform rod AB of length L and mass M is free to rotate about point A. So this is uniform rod. It is free to rotate about this point. The rod is released from rest in horizontal position. So again you are releasing that rod from the horizontal position. Given that the moment of inertia of the rod about A is ml square by 3. Here moment of inertia is also given. The initial angular acceleration of the rod will be. This is same question, right? This is same question. So I alpha equals to what? The torque. Okay, torque equals to I alpha. So how much is the torque? Torque is equal to, so there is this gravitational force acting on it, okay, mg, and it acts at distance L by 2 from A. So torque is L by 2 multiplied by mg, and I is given, I is ml square by 3. Okay, so gets cancelled, L gets cancelled, and the answer would be what? This is same question actually, the last question. Okay, so option B here, B or C? Option C. Okay, so alpha is 3 by 2 g upon L, right? A uniform horizontal meter scale of mass m is suspended by two vertical strings attached to its two ends. A body of mass 2m is placed on 75 centimeter mark. The tension in the two strings are in the ratio is. Okay, so there are two strings. There is a horizontal meter scale. Its mass is m, and it is suspended by two strings. Two strings. So there will be some tension in first string T1, tension in second string T2. Okay. A mass of 2m is placed at 75 centimeters. So 75. So let's suppose this is midpoint O. So 75 means it is at distance of, okay, 3/4 of the length, we can say, right? So this mass is 2 times m into g, we can say, is the weight acting downwards. Okay, the tension in the two strings are in the ratio, right? So then there will be weight of this meter scale acting downwards from this point. So it is mg. Okay, so we need to take talks about some point. Okay, so first of all, we can have two conditions here. So these two tensions should support the total weight. These two tensions should support the total weight. So total weight is how much? Mg plus 2mg, 3mg. Okay, so T1, I can say, from the translational equilibrium, you have T1 plus T2 equals to mg, this mg plus 2mg, 3mg. Let's call this equation number 1. Okay, and then let's call this point A, this point B. So now let's take moments about point A. Okay, taking moments about point A. Okay, so why am I choosing point A? Because I don't want actually two equations, two simultaneous equations. Okay, I mean, I don't want two equations in terms of T1 and T2. So I'm getting rid of T1 if I take moments about point A. Okay, so this distance is L by 2, or you can say 50 centimeters. So moments about point A, how much would be moment due to this mg? It will be 50 centimeters multiplied by mg, right? In what direction? So this is, okay, it's position vector, and this is the force. So r cross f, it is in clockwise sense. Okay, this force is also downwards. Its position vector is like this. So r cross f, this is also in clockwise sense. So plus, you can say 75 multiplied by 2mg, right? And this force is upwards. So r cross f, it is in anti-clockwise sense. See its position vector for this force T2. Okay, it is at point B. It is like this, and force is like this. R cross F is in anti-clockwise sense. So its sign will be negative. So minus 100 multiplied by T2, and sum of all moments should be equal to what? 0. Okay, the body is in rotational equilibrium, right? So we can say that 100 T2 is equal to 50 mg plus how much is this? 75 times 2, 150. Okay, so 50 plus 150, 200. 200 mg, and therefore we can say T2 is equal to what? It is just 2 mg. Okay, and since T1 plus T2 is 3 mg, T1 would be equal to 1 mg. Okay, so 1 mg and T2 is 2 mg. What's the ratio? 1 is to 2 is the ratio. A meter stick is balanced on an eye page. No, this is different. A meter scale, sorry. A meter stick is balanced on a knife edge. At its center, two coins, each of mass 5 grams, are put one on top of the other at 12 centimeter mark. The stick is found to be balanced at 45 centimeters. What is mass of the meter stick? Okay, so there is this meter stick, right? And what are you doing is you are putting two coins. You are keeping two coins one on top of the other like this. At what mark? So this much distance is 12 centimeters. So if you do so, what happens? You can balance it at, they are saying, at the 45 centimeters. Let's use different color. So you can balance this meter scale at 45 centimeters here. Okay, so this much distance is 45 centimeters, right? What is the mass of the meter scale? So its mass will act, its weight will act downwards from the midpoint, from 50 centimeters. Okay, so this is mg, sorry, mg. Okay, and then you are balancing it about this point, right? So let's call this point something. Let's call this point O, or let's call it A only. Okay, this is B and this point is C, right? So these weights you are keeping at point B. Okay, these two coins you are keeping at point, sorry, this point is B. Okay, so now let's take moments about A because we are balancing them about A. So let's take moments about A. So taking moments about point A. So we get rid of this force needed to balance. Okay, so these two weights, or this weight of two coins, it will act downwards. And how much is that? It is 10 times G. Okay, 10 grams times G, because weight of mass of one coin is 5 grams. So mass of two coins is 10 grams. So weight is 10 times the acceleration due to gravity. Okay, how much would be this distance? So from here to here it is 45. This distance is 12. So this distance would be equal to what? 45 minus 12. That is 33 centimeters. Okay. So how much is torque due to these coins? So it is 33 multiplied by 33 is distance. Okay. So distance multiplied by 10 g. This is torque due to coins. And in what direction it is acting? So this is okay. This is the position vector. Okay. This is the position vector, and I mean position vector is directed like this. This is the weight. So r cross f, if you take, it is in anti-clockwise sense. For the other force, that is for the weight of this, weight of the meter stick, it is r cross f, it is in clockwise sense. Okay, so this is position vector. Okay, it's directed in this direction. R cross f is in clockwise sense. I mean rotation is in clockwise sense. If you take r cross f, it will be what? So it will be into the plane of that screen. Okay, but rotation is in clockwise sense. So we'll take negative sign for that. And how much is that distance? Distance AC. So the weight acts downwards from 50 centimeters, and you are balancing it at 45. So this much distance is 5. So minus 5 multiplied by mg is equal to 0 because it is balanced. Okay, so torque, sum of all torques must be equal to 0, and therefore we get 5 mg is equal to 33 multiplied by 10 times g. G and g is cancelled. Okay, so we can divide that by 5, the other side. So 10 divided by 5 is 2, 2 times 33 is 66. So m is equal to 66 and it is in grams. Okay, this is grams, it's not g. Okay, this is in grams. Option B is the answer. Let's see another one. Two children weighing 30 kg and 45 kg wanted to balance a seesaw up length 4 meter pivoted at its midpoint. A child of 30 kg is sitting at one edge of the seesaw. The distance at which the other child sits so that the seesaw is exactly balanced is. Okay, so seesaw has length of 4 meters. So seesaw, this is suppose seesaw, sorry. Okay, one child sits here. Okay, exactly at one end, and his weight will act downwards from that end. Okay, how much is that? So its mass is 30 kg. Let's call it m1. So m1 times g is the weight. Okay, the other child, let's suppose, sits over here, because that other child is heavier one. He will sit at closer distance. Okay, remember mechanical advantage. Okay, so it is m2 times g. So torque due to the first child will be in, it will rotate the seesaw in anti-clockwise sense, and due to the second child, it will rotate the seesaw in clockwise sense. So if we take torques about this midpoint, so we can say that L by 2 multiplied by m1g minus x multiplied by m2g is equal to 0, because torque due to this first force is in anti-clockwise sense, it is rotating the body in anti-clockwise sense, and torque due to the second force is rotating the body in clockwise sense. Okay, so that's why the second one is negative, and therefore x times m2g, or we can cancel out g and g, so we can say x times m2 is equal to what? L by 2 times m1, and we can take m2 on other side, so x is equal to L by 2 multiplied by m1 divided by m2, and that is equal to, how much is L? So L is 4, so 4 by 2 multiplied by m1 is 30, m2 is 45, so 30 upon 45 is 2 by 3. Okay, so that 2 and 2 gets cancelled, right? So it is 30 divided by 45 is 2 is to 3, 2 and 2 gets cancelled, 4 upon 3, so 1.33. What? This 2, I'm sorry, I'm doing some mistake. 1.33 meters, right? Option, yeah, option 1, 1.33 meters. Okay, is it clear? Let's see this one more question. If street light of mass m is suspended from the end of uniform rod of length L in different possible patterns as shown in the figure. Now, pattern A is more sturdy. This is pattern A, pattern B, pattern C. So cable is, okay, cable is connected to this point. In pattern B, cable is connected to this point. In pattern C, it is connected to this point. So point at which it is suspended from the cable, it is different. Okay, so this total distance is L. This is, it's given, it is 3L by 4, and here it is L by 2. So pattern A is more sturdy, pattern B is more sturdy, pattern C is more sturdy. All will have same sturdiness, which is the answer. Why so? So if you take torque about this point, okay, if you take torque about this point, so now the street lamp, it is connected at same point in this diagram, in this one and this one, in all three patterns. Okay, so you have to exert some torque, right? So now if distance of this force is, sorry, if distance of this cable is more, then the tension in the cable will be less. Okay, if cable is closer, then you have to exert more tension, right? Remember the mechanical advantage, load arm and the effort arm. Okay, so here if distance is more, torque to be, sorry, the tension in the cable will be lesser, and that's why it will be more sturdier. Yes, no? Okay, good. So this is the answer. Pattern A is more sturdy. Okay.